So, question number 1 says, define acceleration verbally and mathematically. So, verbally just means like in words, right? So, how would you describe, ready, ladies? There you go. How would you describe acceleration verbally, just in words? Acceleration is changing speed over time, or it's the rate at which velocity actually, rate at which velocity changes. Mathematically, it would be A equals delta V over delta T. What type of quantity is acceleration? It is a vector. What is deceleration? Simply negative acceleration. Awesome. A certain car is accelerating at 5 kilometers per hour per second. Explain what is happening to the motion of the car. So in other words, what does 5 kilometers per hour per second really mean? It means
every second it goes 5 kilometers.
Right. Not 5, oh yeah, did you say 5 kilometers per hour? Yeah. Okay. Every second it goes 5 kilometers per hour faster. Right. Every second it's going 5 kilometers per hour faster. Give an example of a moving object that has a velocity vector and an acceleration vector in the same direction. So give me an everyday example, something that has a velocity vector and an acceleration vector in the same direction, like positive, I guess. Just a car.
Train.
Just a train. Has to be moving.
Moving.
Train going forward, constant speed.
A train accelerating away from an object.
It has to be accelerating, right? Because if there's no acceleration, then the acceleration direction would be nil, would be none, right? So it would have to be a car speeding up, right? Car speeding up. What if the velocity and acceleration are in opposite directions? So one forward, one backward. Well, that same car would then be
Slowing down.
slowing down. So if the signs are the same, both positive, or in fact both negative, it's doing what, right? See, it's both negative. Speeding up just backwards, like in reverse, right? Like making the sound. Yeah. That's the sound. So that's the backing up, accelerating sound. Can an object be moving at a constant speed and accelerating? Oh, yeah, it says yes. Gold. Marley says that. Gold. Why do you say yes and no?
Oh, because it can constantly accelerating. Exact speed. I get what you're saying.
Do you?
But I get it.
It's
Like you're constant, everything, you're going 5 kilometers per hour a second.
Oh, so you're accelerating at a constant rate. But that's not what it says. It says, can an object moving at a constant speed? It doesn't say the acceleration is constant. It says the speed is constant. Megan's got it. Changing direction. The good old St. Rose Corner. If you're going around St. Rose Corner at 100, your speed is the same, but you're changing direction. We're good. These are good. They're not going anywhere. Okay. What would the shape of a speed versus time graph for an object in free fall be? Shape of a speed versus time graph for an object in free fall. Well, free fall means like, okay, got it?
So like, you explained it, so the answer before was yes.
Can an object moving at a constant speed acceleration? The answer is yes. Constant speed, changing direction. Right? Danielle was right, she just had the wrong explanation. Yeah.
It'll be getting faster until it hits
Terminal velocity. But what would the shape of the graph be, rather? You're right, but what would the shape?
angle up and then flat.
Okay, so you mean like a straight line and then
Just terminal velocity. What?
would it be straight and then go flat right away?
No, it'd be like an angle and then go flat at the top.
Okay, so like that?
Yeah.
Would it be sharp like that? This is a velocity, it's a speed versus time graph, right? Yeah, in fact, you're close, you're really close, but it'd be more curved, right? Because as it approaches terminal velocity, it's still speeding up, but not as fast. You're close. Yeah. What's that called? The fastest speed it can fall? Terminal velocity.
So,
Yeah, go ahead.
when I guess before terminal velocity, it like slows, the rate of acceleration slows down or something.
the rate at which it speeds up is less. It's still speeding up, just not as fast. And that's hard to visualize, isn't it? Right? You're falling, right?
Doesn't it get faster as it falls?
Yeah, it does, but then because of the air resistance, there's a force up, right? And so it's still speeding up, but it's not speeding up as fast, but it's still speeding up. It's just not speeding up as fast. Like when you let go right away, it's speeding up really fast at the start. And as it falls, it's now still speeding up, just not increasing in speed as much, right?
Is there any way to make it so that it's not even, like, not speeding up?
Eventually it reaches terminal velocity, and then like you said, flat, then it's just falling at a constant rate, right? And depending on the size of the object, like a football, if you were to drop that, like say off the senior tire ice, it would reach terminal velocity in about 3 or 4 stories. Probably, right? Okay. Something small like a penny might not reach it for like, you may have to go like to a CN Tower penny for it to reach. Did I show you the video with the pennies off the
No.
off the, what's it called?
Empire State?
Empire State Building, yeah. Big sign that says do not throw stuff off, and then they've got like a shelf where there's all kinds of stuff. Because people just ignore it, throw stuff off. Everybody trying to see, throwing rocks in the Grand Canyon.
It's not like you're gonna hit someone on the wall.
There are people down there.
Well, it's a big shot.
Yeah, they go down on their burro.
But what?
On their burro. Yes, their mule. You know what a burrito is?
Yeah,
A little donkey. Yeah. That's what burrito means. I don't know what a chicken burrito is. Genetically weird. All right, number 7. What is the relationship between speed and velocity? Well, velocity is simply speed with a direction. Answer the following by referring to figure 3.5. I think, is that this one? No, 3.5 is way back here, right? This one here. I should almost, can I do it that? Can I cut? I don't know if I can. Let me read the question, then I'll go back to it. Over which interval does the object have its greatest velocity? When does it have its greatest velocity? This is a position time graph. Position time graph. Okay, so think back. Position time graph. How do you find the speed from the position time graph, Johnny? Bingo. Riley's on. The slope. So Riley, when does it? What was the question? When does it have its greatest velocity? So when is this object moving the fastest? Why do you say that? It's the steepest. You're bang on again, man. C to D. What's the next question? Save me going over there. What's the next question say? Object when it's going. Object velocity decreasing, right? When is this object decreasing?
From D to the end.
From D to the end? How do you know? Because it's getting flat, right? And what's the last one? Probably. When's it speeding up?
For which interval was the speed increasing?
Yeah. Okay. So when's it speeding up? From like 1 to 4 seconds at the beginning, because it's getting steeper. You guys remember all this stuff? That's good. That's the point of this.
Yes. I can't remember anything else.
Okay, last one. Sketch a graph of motion, distance as a function of time, so position time graph, that would correspond to the following trip. You start your bicycle from rest and increase your speed until you reach a comfortable traveling speed. I'm just going to do it like this. You continue at this speed for a few minutes and complete your trip by slowing down uniformly to a stop. So, you're speeding up until you reach a comfortable traveling speed. So you're going to speed up. Comfortable traveling speed, that's going to mean it's going to be straight, not flat, because this is position time graph, right?
Yes.
Position time graph, and then you slow down. This is so,
It's acceleration that is just straight line, right? And that's constant.
If this is a position time graph and it's accelerating, it's actually curved. So we're accelerating here, Danielle. This is speeding up. This is constant speed. This is slowing down. This is stopped.
No, but I think like when there's the straight line, like it's horizontal, I guess.
Flat line.
That's the velocity when it gets objects, not moving, but on acceleration.
That means flat line on a velocity time graph, that means moving at a constant speed. Like for example, if we were to draw the corresponding VT graph, what would the corresponding VT graph look like here? This is velocity time. This is speeding up, so velocity is increasing.
And then
It reaches the constant speed, so it goes flat.
not fast.
Yeah, that's true. It would have a little curve to it. And then it goes back down to 0, right? Those two are corresponding. All right, you guys are in good shape. Okay, so you've got two graphs. If you want to work with someone, you can. This is just review. Get you thinking again. Okay. So graph number 1 is position time, right? And multiple choice. Graph number 2 is velocity time. And you can go get a clicker. I have the answers on clicker. Go get the clickers. Okay, so number 1, just listen, you guys. I'll give you a chance to the backside right away. So delta D from 0 to 4. So a position time graph. To find the displacement, you just read it off there from 0 to 4. So it ends up here at, looks like 8. Starts at 2, so that would be plus 6, right? Is it A? Plus 6. We did really well. Only one person looks like it that went up. Delta D from 4 to 6 seconds. Well, from 4 to 6 looks like that bit right there. That's flat. I don't even need to do the math. If it's flat, position time graph, that's a 0. Yay, everyone got it right. Delta D from 6 to 9. So that's this one here. So it ends up, it looks like at minus 4. It's starting at 8. So from 8 down to 0 is 8. And that would be minus 12, I think, right? See?
I'll see what I got this. I'm probably the only one.
We're good? Delta D from 0 to 14. That's this bit right here. It's ending up at 0. It's starting at minus 4, so that's going to be 0 to 14. 0 to 14. So like from there to there. That's like down 2, right? D is minus. Is that the one that doesn't exist on yours? Okay, I apologize. I'll have to fix that. Little boo-bop. V bar from 0 to 4. V bar on a position time graph is the slope. You're finding the slope right there. The slope, remember, is rise over run, so that's going to be 8 minus 2, which is 6. And the run, it's from 0 to 4, so that's going to be 4 minus 0. 6 over 4 should be 1.5, I think. Is the answer B? How we do? Almost. A couple people got it wrong. 6 to 9, that's from there to there, that's negative. That's going to be minus 4. Subtract, that's 8. So that's minus 4 minus 8 is minus 12. Down 12. Johnny and Jeff, are you guys watching?
Yeah.
And the run is from 6 to 9. That's going to be 9 minus 6 or 3. So this is going to be minus 4. B, minus 4. Down, right? Negative. V instant 10 seconds. What does instantaneous velocity mean? It means the slope at that instant. But because it's a straight line, the slope remains the same. So you simply find the slope of that whole line, right? And it's A. It's 0.8. The slope of that whole line.
Oh.
Like you go straight across and read it
If
off
it's
the
a velocity time graph, then you just read it.
Right. Now, what if that graph was curved? How do you find instantaneous slope? Do you remember? Tangent line. You got to draw the line, pick 2 points, tangent. V bar from 0 to 8. So that's from there to there. You have to actually draw that line. So that would be, looks like it's down 2, now we're down minus 6 over 8. Is that it? No, it can't be it. It's B, minus 0.25. 1, 2, 3, 4, 5, 6, yeah? 6 over 8 is not minus 0.25.
Hey, that's not 8, that's 9.
Oh, it's 9?
Put it up there.
Oh, I see, I did, yes. So it's only to there. Right, gotcha. Okay, so you guys did pretty well. So now, some of you have probably done these. Let's fire in your answers for velocity time graphs. That's okay, take your time. Take your time, we'll get her done. Yep.
There's the area. Oh, I feel like you're not giving that what for.
Hello. I forgot all about this. You know what? I could do it.
Megan, could you give me a refresher on
Can I come? No, it's the district. Can I come like at 3:1 today? Okay. I can send it to you down. I'll send it to you down. Yeah, I'm gonna send it to you down right now. Okay. Anybody done the VT graphs already? No. Okay, as soon as you're done the VT graphs, I forgot we're supposed to go into our textbook system. So, as soon as you're done entering stuff, go on your own down to the library. Okay, remember how to get to the library? Yeah. Okay, around back there. Okay, so get going.
Okay, so I got photos.
Yeah. No.
I got it here.
What do you guys get for
You're old. Right. Watch me. Yeah, go get the textbook when you're done.